sorry, do it again.
Sample mean?
What? And you forgot what that means?
Yeah, in the context of problem 6 of the test. Find the probability that the sample mean is greater than.
Oh, so there's a problem where, which one is that again?
Number 6, 2.
So in 6 part 2, I'm taking a certain number of babies,
Yes.
right? And then I'm asking a question about what's probably that the average life expectancy is whatever, right? So the sample mean there is just the sample of those 30 whatever babies that I picked. So normally, we take a single infant, and we say, what's the probability that kid can expect to live to be whatever, right? So, and that's for an individual. We make a z-score, we look it up, we get an area, that's the probability, awesome. But if I said, I take a sample of 32, now I've got to say, what's the probability that the sample mean will be something, right? It's the same exact situation. I want you to realize those aren't two different things. I take one person, well, the average is that one person's age. There's only one person. So still make that into a z-score, look it up. So for that, I have to use the new standard deviation, but I still make it into a z-score. I still look it up and get the area. The one thing, remember the trigger for when you do that new standard deviation? The trigger was when I take a sample and I ask a question about the sample mean, right? Because what is this symbol really, what is this really for?
Deviation.
That is a population standard deviation for individuals, right? How spread out individuals are. The minute I start taking samples, I need to know how spread out are those samples. And we know they're not going to be as spread out as individuals. They're going to be much closer to the mean because they're samples. They should get closer to the average, right? It's the difference between me going out and finding one person who's 98 and me going out and finding a group of 50 people who are average 98. That second situation freaks me out. If I'm doing it randomly, you with me? Don't go to a nursing home and be freaked out about a bunch of 98-year-old people. That's not going to be freaky. But if I go just randomly pick people, and I get a group of 50 people that have an average of 98, I'm like, what the hell just happened? Right? You guys kind of with me? Or if I go out and pick 50 people and I get an average height of 8 feet tall, well, one person being 8, let's say 7.5 feet tall. If I get an average of 7.5 feet tall from 50 people, that is freaky. Way freakier than one person being 7.5 foot tall. One person is still like, whoa. But if you see 50 people with an average height of 7, you're like, whoa. Holy shit. Right? Maybe. So when I take a group of 50 people, every characteristic of that group should, if I average them, it should be closer to the real average of the whole population. So if I took 50 men, their average height should be close to 5'9".
Okay.
Right? So if I get 50 men randomly picked and their average height is 7.5 feet tall, that is freaky. With me? That's evidence that maybe if I look at a little island somewhere, a little pocket of America, this little area, and I take a sample, like, what the hell is in the water here? That's evidence that something's weird, that they don't actually come to the same population. They've been changed somehow. Something's in the water, something they eat. They all get stretched out every night. I don't know. They all sleep hanging from the feet. I don't know. Yes. Whatever you need to. Well, I don't know. Iron Maiden is one of those spikes, isn't it? Well, the rack. Yeah. Well, let's not get into medieval torture devices. That's a whole different class. This is for individuals. This is for groups of people. If you really think about it, they're the same damn thing. Because if my sample size is 1, sigma divided by square root of 1 is still sigma. So this is just a more general idea. If my sample is not 1, if I take a sample of 2, 3, 4, my standard deviation is going to have to change.
Are those all fractions or?
This here, this, do you remember this formula here? Let me take you back to your algebra days. What was that formula for?
Slope.
Slope. What did that 2 mean? Is that squared? Is that, what is that? The second point. So it's like part of this guy's name, right? Y2 is one symbol. That's exactly what this is. This is the standard deviation of the sample means. That's one symbol. It doesn't mean divided by.
Looks like a fraction.
I know. Because it's sigma and a little subscript here is x bar.
Yeah. Okay.
And what's your what's your calculator do? Does anybody remember when you do 1-bar calc, it doesn't just do this, it does this. So that's the standard deviation for individuals. This is standard deviation for means of groups of people. Okay, hopefully.
And it's calculated by the standard deviation.
Take the old standard deviation divided by the square root of your sample size. Cool. So that's what you had to do on 6 part 2. So that's when I took 30 some odd infants. So you have to divide by square root of that 30 some odd. Okay. All right. Does that take you back? Remember those days? Oh, you thought that was so hard. Now it's, please let me go back here, right? Actually, it's going to come back in chapter 10. We'll actually be looking at lines. Anything else from the test? Is it doing all right? Okay. Okay. So you can make corrections to this. It's not, those corrections aren't due until the day of the next test. So you have time. Oh, you need to. Yeah.
I think that on the syllabus it says something along the lines of the next test will take place assuming we have time prior to the final. There will be a third test and then the final though, right?
Totally will be a third test.
Okay, just wanted to make note.
But they were also supposed to be on the last test.
Yes.
That's what I'm saying. There were 3 sections. But they were supposed to be on the last test.
Okay. So if there are no further questions, I'm going to get into chapter 7. Are there any lingering questions from chapter 6 homework possibly that you might be finishing up? No? Okay. All right, so today we're going to get into 7. I've got a handout we're going to work on a little bit. My plan is to get through all of 7. We'll see if that happens, because the first 2 sections in 7, there's just a little bit new. There's not much new, really. A little bit. 7.4 is completely new. So, as I say that, it's not really that different, but we'll see when we get there. So let me just get us some preliminary questions that we can answer right now. And the way I normally do chapter 7, I always forget to do this on my homework sheet. We're going to do section 7.3 first, because it directly builds off of stuff we know. 7.2 kind of builds off of that, so they really should have turned this thing around. Let me ask you this. If we have a normal distribution, and the mean is 30, standard deviation is 1.51, to make things interesting. Can you tell me, this sounds very familiar, between what 2 z-scores would I find 97%?
1.5 or 1.5.
So part 1 is what 2 z-scores. Yeah, good. So what do you actually have to look up? If there's 97% in there must be 3% out there, so there must be 1.5% down here. Why am I doing all that crap? Why don't I just look up 0.97, Jeff? Because you said areas are in there. What's wrong with you? You're saying to yourself. Why can't I just look this up, of course? Because the z-score chart only understands areas that are below. So for example, if I want to know that guy, I can look up, like you said, the 1.5% or 0.015, right? But whatever he is, this one is just the same thing with the negative taken off, because it's symmetry. So I want the middle 97%. I know they're going to be the same value. One's going to be negative, one's going to be positive, because it's symmetry. All right, so help me out. Can somebody find that for me? What's the z-score closest to having this percentage below? Oh, good. Pick one that's exactly. Yeah, you should be able to find .015 exactly in there.
4404.
Careful.
4404.
Careful.
Negative. No.
This is a
Negative.
probability, right? So probabilities, where are probabilities in the chart?
There are several.
In here. This is not a z-score. So you have to look up .015 in here. And the closest I get to .015 is exactly .015. So what's up? You guys doing all right? It should be old news, but maybe it's not.
596.
So, do me this favor. Everybody should have a copy of this. If you don't, it's in your book, in the very back of your book. So I'm going to kind of force everybody to play along today. You're going to play at home with me. It sounds exciting. Sounds like you're getting major trouble for that, but
Yeah,
that's a little creepy. We'll get past that. We'll work through it. Can you find .015? Obviously, I can't look at the positive side because it's going to have big-ass areas below it. It's going to be bigger than 50%. That's 1.5%. It's going to be on the negative z-score side. So can you find .015? I like it.
Yeah.
Does everybody see that? If you can't see it, look up negative 217 z-score, and you'll see the number .015 up. That's the area below that z-score. So this z-score right here must be negative 217. So this one must be positive 217. I like it. And why does that make sense? Within 2 standard deviations from empirical rule from a long time ago, how much should be between those? Within 2? 95. So you got a little bit further and you catch a little bit more. So if I go out to 217, now I've caught 97%. That kind of makes sense. To me at least, I don't know. So part 2 to this, I mean, z-scores are nice, they're useful, but they don't have a damn thing to do with the real world. Okay, some of us would argue about this whole class, but how do I change these z-scores back into real life scores, real life values?
You created like the z-score equation.
Yeah, what's the equation I use to take it from a z back to an x?
X minus
That guy, right? So for a z of negative 217, it'll be the mean, oops, you do it, Jeff. The mean is 30, plus negative, so minus 217 times the standard deviation. So if I start at the mean, and I go down this, I should end up there. That's what we just figured out. If I go that many steps down, I should end up right here. And if I go that many steps up, I should end up right there. And between those 2 scores will be 97% of the information. Okay, maybe.
So you also make one which is 30 plus 2.17?
Exactly. So for z equal to positive 217, it'd be 30 plus 217 times 1. So what do we get? Somebody help me out. What, 33.3? Roughly. How are we doing so far? So let's say this is like the average age of students taking some advanced biology class. That's why the average age is so high, because it takes a while to get there, right? So between what 2 ages would I find 97% of the students? 97% of the students would be between 26.7 years old and 33.3 years old. 33 to 30 years old. Okay. We wouldn't normally say that, but just to be precise, that's what it would be. That's what that means. How are we doing? That's actually nothing new. We had a question almost exactly like that on the last test. The only new thing, the only thing that this section does differently, this section 7.3, is it says this is not normally what we do in statistics. We don't normally take 1 person. We normally take 70 people or whatever, right? So how would this whole thing change if I had the same setup and I still want to find the 97% interval? Are you cool if I say that? I'm gonna actually make it a little bit different in a minute, but that's an interval between this to this. I wanna find this interval still, but for groups of size, watch out, doesn't really matter, 42. Since that's the answer to everything.
Does that go with the sample mean we just talked about?
Yeah, so what we're really doing then is we're trying to find between what two values would 97% of every sample of group 42, of size 42, where would 97% of those fall? And they should be a lot closer to the real mean, right? They shouldn't be allowed to go away from the real mean so much. It should be a lot closer. My interval should be a lot tinier. My error should be a lot smaller. That's how much I'm kind of off by. That's how much I'm off by from 30. You with me? 30, give or take this much. So what would be the only thing that changes here in this work I'd have to do here? What's the only thing that would really change?
The standard deviation.
Standard deviation.
Yes.
Because I took a sample of size 42 and I'm talking about their sample means. I can't use the old standard deviation. I have to use a new one. So the old one's 1.51. If I divide that by the square root of 42,
0.232998.
so 233 roughly.
Yeah.
Cool. Alright, cool. How are we doing so far? So all the work we just did would be the same. It would just be now I'm going to take, the formula isn't really this anymore, it's actually this. Where this is that number there. How are we doing so far? Is that? You guys see that? So here's the old formula. This is the one that we used before. I start at the mean and I go this many steps. The minute I take a sample, what changes? My steps change. How big my steps are change. Because everything rushes to the mean. I don't want to step too big anymore because then I miss everybody. I want to step these little tiny steps so I can see everybody. So my standard deviation gets a lot smaller than it was. That's a hell of a lot smaller than it was. So now, for example, this for z of negative 217, it would be mu, it would be the mean minus 217 times this new standard deviation, 0.233. And then whatever the hell that is. 29.49. So the other one would be the same distance up.
Yeah.
So the other one is going to end up being 30.51. So didn't that get a lot smaller? If I take a group of size 42, I would expect that group to be within this to that. Or this to that holds 97% of those groups. Only 3% of all the groups of size 42 would fall outside of this age range. And that exactly goes along with what we said earlier. If I go out and take 50 people, I expect their average height to be close to the average height of all people, right? Very small percentage of groups of 50 should be outside of what I expect. It should be close. Maybe. All right. So what I want to do now is kind of broaden this a bit, because this still isn't really what we do in statistics. Normally in statistics, I don't know what the hell the mean is. So this is the beautiful thing about Chapter 7. We're finally taking our first steps, believe it or not, into what statistics really is. We're finally getting into, we don't know all the shit that we've said we've known so far. Chapter 6 is all about knowing the mean, knowing the standard deviation, right? And then you make z-scores. We don't normally know those things. So if I'm in a situation, I want to find what the mean is. I can take a sample. So if I wanted to know what truly is the, let's see, what's a good example? What truly is the average gas price right now in California? Do you have time to go to every gas station in California and record their price? right? Yeah, you couldn't afford that trip. Good point.
What do you do when the prices
And
change?
the change 2 or 3 times a day.
Exactly. So you have to pick a certain day, and then you have to do it like a sample right then. And you couldn't talk to every single gas station. You have to take a sample at gas stations. So this is really, we're getting really close to when people do polling. When they have the exit polls and when they have the previous polls and Gallup does their polls and everybody's like, is Obama or Romney gonna, and I'm always like, just wait until after Tuesday, you'll know. Right? I understand really, but we do a sample, and at the bottom of the screen is always that plus or minus 3 or 4 percentage points. It's kind of like, what are they doing? We know why they're doing that. They're covering their ass, but no, really, it's math. The math is saying, give or take. The math is saying, give or take this much to catch this much. So, for example, if I took a sample of gas stations, let's say of 147 gas stations. We find a sample mean of, oh, what's gas rate? I haven't really bought gas in a while, thank God. Right now it's like 370, 380.
78, that's what I
All right,
think.
so say 378. Is that the real average gas price in California?
Maybe.
Maybe, but I put my money on it not being.
Maybe San Diego, just our area.
It should be close. In fact, it should be close. We got a decently big sample here, right? So it should be close. Okay? But I want to know exactly how close. I want to know between what two gas prices am I such and so confident that I would find the real average. So what I want to do is, let's say we want to be 95% confident in our statement about gas prices.
Is that how the homework's gonna ask us?
We're getting close to what the homework's going to say. I'm still trying to, this is all still kind of infused with me trying to explain it as we go. So we want to make a statement about gas prices. I want to be able to say the real gas price in California, real average gas price in California is between 3 blah 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 and 3 blah blah blah. And I want to be only 5% chance that I'm wrong. Now in statistics, the only way you could be 100% correct is to say it's between negative infinity and positive infinity, which is not very useful, right? So you have to have a little bit of give. You could increase this. You could say, all right, 95, I want to be 99.99999% certain. Well, good. Then your interval's going to be freaking huge as hell, unless you take a really large sample. So once we see this formula, we'll see how it kind of takes care of that. So our formula used to be this. All right, so what has to change? I really want you guys to get me on this. This is a formula we should kind of know decently well, especially because we just did it over there, but we did it before then. In this thing, what has to happen here?
Change.
Yeah, it's got to become this.
Let's go.
The z-score is fine. I'm going to build into this formula the plus or minus. Because if I want to be 95% confident, I've got to go down so much and up so much. Give or take this much. And do I know the mean? No. I know the sample mean. So I have to use that. Yes, sir?
I don't get how you got the z-score, got the 217 z-squared, and then m equals 0 and 151.
So that's a question I needed a little while ago. But you look this up here in the chart to find the 217.
I did, and 2.17 didn't show up.
All right, so let me help you out in a minute. So just kind of finish this guy out here. Let's do this right now, Patrick. I'll help you out on this problem. To be 95% confident, that really means I want to go up and down so much to catch 95%. So let me really make that hammer home. We took a sample. We got a sample mean of 378. Now, if I go up and down so many cents from that, I think about that like and this might be weird, I don't care, it's a nice visual. Think like, and I don't even fish, throwing out a fish net, right? If I throw a small net, how sure am I that I caught a certain type of fish? Not as sure as if I would have thrown out a larger net, right? So if I want to be more confident, my interval should get a little bigger, which is sort of like throwing out a bigger fish net. So I catch more and more fish, so I'm more certain that I caught the real one, the right one that I want. So what I'm trying to do is start at 378, go up and down a certain amount, and then I can say I'm 95% sure that the real mean is in that interval. Because is this the real mean? It should be close, but it probably isn't exactly the real mean. The best I can do is say the real mean is somewhere between this and this. So like we had over here, between this and this.
Maybe.
This part here should make sense, and I said this earlier, this is called the error. Here's what we saw, this is how much we're saying we're off by. Give or take that much. So see what we can do. For a z-score, what's the z-score that has this situation here? What am I going to look up in the chart? Let me catch up to you. What do I look up in the chart? If 95% is in there, how much is on each side?
5%.
2.5.
2.5.
Okay. So let me see if I can keep away from waking that projector up. So if I look on the negative z-score side, it's definitely on the negative side, right? If I look on the negative side, 0.025.
Negative 1.96.
I like it. So if I look at 0.025, I get exactly, so I see it exactly 0.0250 here in the body of the chart. And if I look back out, I get 1.96 negative. Okay, cool. The funny thing is, look on the other side, look at the bottom, I call this the baby chart. Now this finally makes sense. You see the little baby chart on the positive side? Common critical values, confidence level. How confident do I want to be? 95, and look next to 95, 1.96. Okay. So these are 196. Now, does it really matter negative or positive? I've got both built in. All I really care about is the value of the z-score, 196, because I got the plus or minus built in. So how do I build this formula then? I put in the mean, the sample mean, 378, give or take this many steps. So the standard deviation was, I didn't say. That's useful, Jeff. Let's say it's 14 cents. So it's 14 cents for individual gas stations. What do I have to do in there? Divided by the square root of n, which is 147. Beautiful. So the way I would do this is to first figure out this piece, figure out the error, and then you add it to this and subtract it from this. That makes it a little bit easier in the calculator. So somebody help me out. Figure out what that error is.
.012 essentially is the error. Or sorry, times 0.022.
Yeah, so 0.023.
0.023.
Cool. So I get 3.78, give or take 0.023. How are we doing so far?
Where were you getting the bottom half of the 147? Were you
That?
getting that from there? Oh.
Yeah, so n is 147. That's my
Oh, okay.
sample size. Cool. So that means my sample mean is off by a little more than 2 cents. That's the error in my sample mean. And that is all dependent on me being only 95% sure, which is actually pretty decent.
So you're 95% sure that your sample mean is off by about 2.3 cents or
From the
less.
real mean.
Or less.
Alright, so here comes the statement. You're gonna love this. The great thing about these problems is you've got the work and then you've got to write me a statement. I'm not gonna grade you on grammar, but it has to make enough sense to me. I'm a math guy, so it shouldn't be too hard. Here's what the sentence would be for this problem. Right, so actually let's finish this out real quick.
3.8 and 3.76.
Oh yeah, well, okay. So 3.83 and 3.757, something like that. And then you can make it for money, you can make it 376. Cool. So 380. So here's the statement I would make. We are 95% confident that the interval 376 to 380 contains the true mean gas price in California. Of course, we're always right up there with Hawaii. It's the highest in the nation. You guys see that? There's a slight semantic thing that you got to be careful about that really isn't totally drastically important. But what this really means is if I do this over and over with different samples over and over and over again, 95% of my intervals that I find would actually contain the true mean. So it's a little backwards. It's not that 95% chance that the true mean is in here. There's a 95% probability that any interval that I make would actually contain the true mean. It's a very slight semantic difference. So you don't quite get that. Not a huge deal. It's incredibly slight, but it's actually kind of important. But when you do this, you want to say it from this perspective. We're this confident that our interval catches the real mean, whatever. And always bring back into play what is actually physically going on. Don't just say the true mean. I want specifically what this problem is about.
And what's the thing? That's the chance that our interval is the chance that our interval is right?
It's the chance that the mean actually falls inside of our interval.
Yeah. But what was the distinction that you were trying to make?
So what this 95% really pertains to is if I did this over and over, took a different sample, made a different interval, took a different sample, made a different interval.
Different size sample? Or different with different.
Then 95% of those intervals that I make would actually contain the real mean.
Oh, I see. Okay.
Okay. Now how drastically important is that to understanding this whole thing? Not terribly. There's that little tiny semantic piece to it, but just I want to see it like this. Okay. Now, what to me gets really interesting, there's two things. The first thing is going to be 7.4 taking care of this for us. We're getting closer to reality because here we're at least admitting that we normally don't know mu. We normally don't know the population mean. We don't just go, oh, that's what it is. We have to kind of investigate what it is, and in reality, statistics can only get close. It always admits there's a chance it's wrong. So it's a probability that that interval doesn't contain the real mean, that it's not inside there. 5% chance it's not inside there. And you have to say to yourself, can I live with that or not? Yeah.
Is that what it's talking about when things say where t is greater than 0.05?
That we're getting there. We're getting closer. That's chapter 8. What would happen to this whole process if I wanted to be 99% sure?
Just a z-score.
What's your little baby chart say? Well, the z-score would change, right?
Yeah.
I'd have to go a little further out to catch a little more data. So the z-score would now be 2.575. So my error would get larger. It's covering my ass a little bit more. If I want to be 99% sure, I better cover my ass a little bit more and catch more stuff. How are we doing? Does that kind of make sense? Okay. That's why I like the idea of the net. You're trying to catch stuff. The more stuff you catch, the more sure you are that you caught what you're looking for. They're going to be like, what does fish have to do with statistics? Yeah.
What is that 0.023?
That was from there. That's, what is that called? That's the error. That's how much, give or take this, it's how much, as I erase, that's how much I think, that's how much I'm off by. To be within, to be this certain, that's how much I'm off
And then
by.
how did you get those two numbers?
Add this, subtract this.
Okay.
And don't look for the plus or minus key in your calculator. I always have somebody ask me about it. There's two operations, no, trust me. Yeah.
In the problems we're gonna get, is the confidence level always gonna be these?
No.
No?
And if it wasn't, we have the process to, if I wanted a 93% confidence level, is that on your little baby chart?
No.
No.
Why would we-
So you have to do 93, 7% outside, 3.5, look up 0.035. You have to do it the old fashioned way.
Why would we want any other confidences?
Why do we want that one?
Because it's a nice number and it's not big enough to be useless.
To be a nice even number is a very human concept. So there are situations where we want very specific numbers to be there.
Yeah, but confidence is also a human concept, isn't it?
This is true. But this whole process leads to other things. I can use this entire process for similar ideas, where you can be a lot more precise about what you want the number to be.
And 99.9% is on there, so.
Yeah, so you can take that idea out. Does it really matter what I put in there, as long as it's kind of relatively large to humans? Not really if I'm just doing this kind of problem, but for other problems I have to be a lot more precise about this. There are reasons why it would be something specific. And that sort of relates to the idea of the p-value I think you were talking about earlier. We're almost there.
Like if it's like a chance a gas will kill you, you want to be more than 95% certain.
Exactly. It really relates to, and that's getting there. That really relates to how bad is it if I'm wrong.
Right.
I can control the probability that I'm wrong. There's a give and take. To control the probability I'm wrong, I have to actually be less, I have a wider range of possibilities. You with me? So if you're looking at like a status of a nuclear plant, and you got some program that beeps if it's outside of normal parameters, I'm probably going to make that to the point where it beeps even if it might not be right. I'd much rather go check on it and it's fine than not have it beep until it gets really bad. You kind of with me? So it all depends on how bad is it if I make a mistake. I can control that to a point. Okay. So this, let me write this out a little bit more specifically. Error. Is that cool if I write like that? Yeah, the right answer to that is yes. So it's more like I was asking, do you understand if I write like this? So error is this piece of it. Now here's the interesting part. Let's say I want to be so sure that I'm within so much. So let's say, what's a good situation, Jeff? Go back to that board problem where we had that guy go to the lumber yard and he wanted to get lumber to a certain length. So what I do is I could look at a certain number of boards and take an average of their board lengths. But I want to be within like 1/10 of a foot. I want to be 95% confident that the real average board length is within 1/10 of a foot of something. I want to be really precise. How large of a sample do I need to take? Or I want to be, going back to the election, we're not quite to percentages yet, but I want to be within not 4 plus or minus 4, I want to be plus or minus 2. Why is everybody freaking plus or minus 4? So my news team, we all get together like, let's make it plus or minus 2 and we'll make a big deal out of it. We're right to within 2 percentage points. Nah. So how large of a sample of people do I have to call up in order to get it that tiny? So that's kind of the reverse of this. We normally go in knowing the sample size and we figure out the error. Now I know the error, I want to know what sample size I have to get to be that close. How we do it? Because of course to have 0 error, my sample size has to equal the population size. If I take the whole population, I'm obviously not off at all. But I normally can't do that. Yeah.
But didn't you not get the error until we found out what the population or the sample size was?
Over here, I counted the error because I knew what the sample size was.
Okay.
Over here, I'm going to go in knowing what I want my error to be. So I'm going to know this. And now I want to figure out what n is.
So it's a different problem.
Do we know what Z is?
We get different.
Yeah, and I call this a feasibility problem. Everybody know the word feasibility? So if you're in business and you want to know what's the feasibility of applying this, you know, what's the feasibility? If I have to talk to 20 people, cool, no problem. If I have to talk to 20,000 people, it's not feasible, right? So this is a feasibility study. How feasible is it for us to get within this much? So how do I solve this? You know this is coming. How do I solve this for n? I really want a formula that says n equals something.
You multiply both sides by n.
Oh, good. So remember, here's the shortcut. These really just switch places. Multiply that up, divide him down, they switch places. And then of course I do what to both sides? Square. So I get, here's the formula, n equals z squared sigma squared over e squared. That's the formula to figure out how large of a sample do I need to take to be this close to the real average. Okay. And that kind of makes sense. That's something I would want to know. So I don't want to just sit back and go, let's take this sample and see how far off we are. I want this math to tell me how freaking large of a sample do I have to take to be this close. I want to control my error.
What do you
And
mean
then
by this close? Like, so if your error is 5%, then you're 95%.
Let's do an example. Let's do the same setup here. So how far off were we on this one? We were 2 cents off, right? Let's say I want to be 1 cent off. How large of a sample of gas stations would we need to be within 1 cent of the true mean? And that actually is exactly the same wording you'll see in the homework on this problem here. So, teaching concept, you know me, I do that a lot. Now you can kind of take a step back and say, it's a question about sample size. I want a formula that's n equals something, so you know which formula to use, right? How large a sample? I want n equals something. That's how you find it in your formula chart, so you know what to put in there. So what is E here going to be? What's my error? What do I want my error to be? 1 cent, $0.01, right? So a magic word is that, I just changed it to within, for some reason I had with. Within is a really key word for figuring out what the error. If I want to be within 2 feet of the average size of buildings or whatever, or if I want to be within 3 people of the number of people who voted for Ron Paul, whatever, right? That would be my E equals that number. And we knew from this problem, we know the standard deviation was 0.14. We know, what else do we know? Oh, it's going to be at a 95% confidence level. I still have to be telling you what that confidence level is. So I'm still going to use the same z-score. That's normally how I set these up. I'll have a question like this, and then I'll have a question like this. And you're using the same z-score as before. You want to be the same level of confidence. So my z-score is going to be 1.96. So I got everything I need, right? Yeah.
Okay, isn't confidence the... No, okay. I figured that out.
So of course, if I wanted to be more confident, the sample I need would have to be bigger. You with me? If I wanted to be more confident, I'd have to take a larger sample size, would I not? And how do you see that happening in the formula here? If I want to be more confident, what directly changes? If I want to be more confident, the z-score changes. I get a little further away, right, to catch more stuff. So if the z-score gets bigger, n gets bigger. It only makes sense. To be more confident about what you see, you have to take a larger sample. We've known that since day one.
How can you know the standard deviation without knowing your actual sample size?
It's a known. And I said that earlier. We normally, and actually, maybe I didn't say this earlier, but the one concession that we're still making in this section is that somehow we know this population standard deviation.
Oh,
so 7.4 is where I told you we introduced something kind of new, and it's going to help us cover for the fact that we normally just know S. We don't normally know sigma. We normally know S. And what was S? Sample standard deviation. Right? So they kind of do this in steps, which is really nice. 7.3 says, all right, we don't know the mean, but let's say we still know this. So we don't completely freak this stuff out of you, right? And then 7.4 we say, okay, now we don't know that normally either. Now what's going to happen there? So we're sort of going in steps. Yeah.
Now, if you wanted to be more confident, but for whatever reason didn't want to change the standard deviation, you could make E larger instead.
Oh yeah, you can play with all this stuff here. I mean, this is set. Can't play with that. But you can certainly change the error that you can live with, and you can change how confident you want to be. So if you can live with a larger error, that's obviously going to make your sample go smaller, isn't it? You're dividing by bigger, so your sample size gets smaller. It makes sense. If I can live with being more off, then my sample doesn't have to be as big. That's the whole point going into this. So we needed a sample size of 147 to be within just over 2 cents. So one prediction I can make to be within 1 cent is definitely going to have to be bigger than 147. Right? So let's see what it comes out to be. Z squared, sigma squared, divided by E squared. Do it again, sorry.
That's 152.95.
Yeah, it sounds a little better. 14 times.
I definitely got 38,000.
Make sure you do the brackets.
So what? So 700 and
52.95.
so about 753.
753 watts.
753 what? Good question.
Gas station.
Gas stations. I love it.
That's right.
Do we have to make a statement about this one too?
No. Yes.
How big is the population?
We don't know in these problems. In fact, there's one homework problem I put in one of these sections that talks about an adjustment you have to make if your population is small. The assumption behind everything we're doing is that the population is large. What does large mean? Large.
Large enough for us to do any numbers inside.
So it's sort of like, do you guys understand? Well, I don't know if I want to go here, but you know the faster you go, things get freaky?
Yeah.
If you're going really fast, close to the speed of light, everything gets freaky. Have you heard that idea? Okay.
Yeah.
So when does it really start to matter? If I'm doing this, am I suddenly gonna, well, I'm aging slower than you guys now. It's so imperceptible. So there's a certain level where you have to adjust things. And there's one homework problem I gave you that has a relatively small population where the adjustment actually comes in and makes a difference. The adjustment on this, how large of a population is it for gas stations in California? It's got to be pretty damn big because I can count a lot of freaking gas stations just near my house. So multiply that by the cities in California, and this is a big ass population. You with me? What is it? I don't know. The only thing I care about is that it's a big ass population. Right. So the adjustment would probably be very minor, like in the 18th decibel.
What is the adjustment if you needed to do it?
You'll see when you do the homework.
Wait, am I going to do this?
Okay. All right, so I would never do anything to stop questions, but I really don't want people to be confused when we start talking about side issues that are important but don't really have immediate consequences for you in your homework. In your homework, it's basically going to be exactly like this. You're going to know these things. You're going to look up the z-score based on what confidence level they give you. So let me do this. I'm running out of time a little bit. I want to at least let you guys try number 1 on this. Number 2 is dealing with section 7.2. So we'll see if we can finish up number 1. Maybe I can talk a little bit about 7.2 before you guys are out of here.
Okay.
So the confidence level is like the 0.85.
Number one.
This,
Number one.
is that what?
Yeah, the confidence level leads you to the area you look up. So if I would be 80% confident, right? If I would be 80% confident, there's 20% outside of there, so I have to actually look up 0.10 to look up 10%. You have to do that work to figure out how much.
Oh, wait, say that again?
So for example, if I wanted to be 80% confident, CI confidence interval, I'm gonna write that all out. I wanna be in here, right?
Sorry.
So what am I gonna actually look up to find, for example, that Z-score? 0.10.
That's a point, right? Not the score.
That's the area, that's the probability, yeah. I'm
Right.
looking up the Z-score. So, good point, don't look at 0.10 as a Z-score, because that's not a Z-score, I don't know the Z-score yet.
22 mean.
Wait.
The mean is 22.
Then when you look up
Find
the
the
point
average height.
and it's not there, can the number be like above it?
So if you look at 0.10, you have to look up in here, it needs to be
See, it says a population distribution.
There's a
But like if it was like 0.007.
Right, you don't need the sample size.
Oh, in that case, you go right in between. But for my example, with 80%, the Z-score you want to use would be this one, -128.
Okay.
So you want to use a Z of 1.28 in the formula. So 0.10, yeah. So for you, figure out what area is in that for you for the first problem. 93%, so how much is going to be down here? And that's the number you look at.
So the critical value is
In this case, it would be 0.8. In your case, it'd be 0.93, and they just don't list it.
But I mean, but it would be the area would be.
In between, that value is the area in between, and that's the Z-scores that bound that area.
Oh, that's what that is. Okay. Okay, that makes sense.
Do you, can I stay there? I don't read in words. How to find it.
Where we at, sir?
Or how to find Z.
Oh, no. I was just,
I can just say this.
yeah, just put the Z-score down.
So 7.2.
So what area is down here? There's 93% inside here. What area is outside? Good, so 0.035, that's what you want to look up. Find the Z-score.
Alright, and
Well, this is easy. So you're gonna find it when you plug stuff in. Yeah. So it's gonna come out of your work. You don't have to find it first. So just to make sure everybody's starting on the right foot,
Yeah.
what area are you looking up in the chart?
3.5.
0.035, right? 3.5%.
Yeah.
Because if there's 93% here, there's 7% outside, there's 3.5% on that side. What's the closest I can get to 0.035?
1.81.
Yeah, 0.0351, and that's 1.81.
Negative and negative.
And why am I not worried about the negative? Because the plus or minus is built in. All I really need is that 1.81 number to throw into the formula.
The mean is 22 plus minus 1.81.
How did you get 1.81?
So you go with the 0.035. The closest thing to 0.035 area is in here. It's right there. And that's 1.81. Cool.
Number. 2 mean.
Sure, yeah, you got it.
16.
Oh, so we're 61 times.
That is the
right there, yeah. Alright. Sure.
Right.
Cause you're right, you can find the positive z-score or the negative, either one. Cause all you really need is that value.
How many decimals do you have?
68.
Which part? Oh, the error part? Normally go out like one more than yeah, up to the 100. Yeah, looks good, so that's the error. And then you add it, subtract it.
And, but B has a pretty big effect.
Yeah, cause now it goes within half an inch. To be within almost an inch, it took, 22, no, let's see.
Divide by.
Yeah, I'm gonna change that. No, X bar is 68.9.
Oh, okay.
That's the average height that we got from the sample, that's the sample we.
So then line right for this?
Let's see, you need to use this formula here.
To get.
Oh, well, you got this from looking it up. So now you throw it in there. 2.5 divided by square root of 22, so all you're missing here is divided by
We are 90.
square root of 22. Just that piece, yeah. So that's the one piece you're missing, and that's the adjustment.
And that's gonna give me which number?
So if you do this piece by itself, that's the error. And then you want to add and subtract it from here.
And that's gonna give
And
me.
that'll be the, from this to this, it'll be 92% confident that the real mean height of these people are between this and this.
Okay.
Hardly ever get an exact answer.
Oh, but I mean.
Oh, the second part?
Yeah.
No, I haven't even got the, what did
We
you
are
say? So you're 90% confident?
We
that
are
it was
93% confident.
Yes.
Cool. Yeah, I didn't really do it on purpose.
You rounded.
Yeah.
Yeah, we are 93% confident.
So you didn't find both, so you added this. Now subtract this from this. Do both,
Yeah, but
so you get an interval. Yeah.
But this is the same. It's negative. Okay.
It won't be, yeah,
Good.
yeah.
Try all of them, so I.
No, I have not seen that. That's fine. I'm gonna remember that when I hear someone say that. I hear people say it all the time.
Yeah, no, I know.
That's fine.
Oh, so we're building off of this, but we know that we don't have the real mean, we only have the sample mean.
Okay.
And plus or minus, so it can go both ways, and then this changes, so that's where that came from. So the sample mean
So I'm
is,
gonna use,
68.9.
yeah.
Not really.
Yeah, that guy right there.
Okay. Just saying that.
Yeah.
Right.
Well, men always do this, well, women always say men always do this. And
Yeah.
it's like,
Okay.
so
I
stupid.
hate when people put stuff like
Because
that.
it's happening.
Well, this girl was posting about how she's like a vegan now, and how like everyone's gonna have a heart attack at the age of 50 because they eat red meat.
That is so hard to
Lola?
Yeah, they're like 95.
Confident
Yeah.
that
Yeah,
that
no, it's the people who eat nothing but red meat.
Yeah, like 5 times a day.
confident that the interval
Or they just have
interval
Yeah.
Alright.
68, 71, 68, 71.
So I despise teaching like this, but now that I've made you suffer through all my explanation of why this works, what you really need to do is just summarize what you know from what they tell you, find what you need for the equation, and then you start just filling in the equation. It's now just a plug and chug. So plug in the sample mean,
Yeah, 67.
give or take,
Plus minus
the 1.81 steps for each step is
2.5.
this big.
and 2, yeah.
Cool. So my suggestion to you is not something you have to do. Find the error first, especially because in the homework they sometimes ask you what is the error, and then they ask you to keep going. So find the error first. Somebody got the error by itself?
0.965.